TRC. Yeah, maybe we should start if you start recording. Yeah, it has a lot of advantages, so I highly recommend updating. Yeah,
Okay.
I can also show some of the updates later.
Okay, cool. So yeah, I think we can get started. So uh hi everyone. So welcome to attend our optical photonic computing system seminar. So this is our eighth seminar. It will be 1 hour, including 45-minute presentation by the speaker, and then finally 10 to 15 minutes in the end for Q&A. So if you haven't registered our mail list, please scan the QR code so you can receive our emails for more events in the future. We also have this Slack channel for networking and potential collaborations. Our YouTube channel is used to post past events, video recording. So please feel free to share it with other people to review if they cannot join online. And finally, some logistics. So the event will be recorded, and if the presenter agrees, then later we will share it on YouTube. So if you have any question, please type it in the chat box. We will moderate the QA session in the end, and the speaker will answer them. Okay, so so today we are very glad to invite our eighth speaker, Dr. Joaquin Matres. He will share with us his work titled "Revolutionize Your Chip Design with GDS Factory." So I guess in the audience, most of people will need to do photonic device fabrication, and definitely GDS Factory is a very cool tool for fabrication. So definitely, we are very happy to invite our speaker here. And so the bio is Joaquin has designed chips in Python for 15 years in companies such as Intel, Hewlett-Packard Labs, PsiQuantum, and Google X. Joaquin started the open source GDS Factory project in 2019 to build better chips in Python. Since then, it has been downloaded over 2 million times. Joaquin also works closely with the open source developers at Google with the Build Your Own Silicon program, where they are trying to repeat the successful ecosystem that open source TensorFlow has created for machine learning since 2016 into building open source chip design tools. Okay, so thanks very much for the great talk and in advance, and the floor is yours.
Perfect. Let me share my screen. Hi, everyone. Yeah, I see a lot of people. So that means 45 people looking. Nice. Yeah, so can you guys see my slides?
Yes.
Okay, perfect. Yeah. So today I'm going to be presenting GDS Factory. So I started GDS Factory over 5 years ago as a tool to make chip design easier. So GDS Factory came because most of the other tools I used in the past were not user friendly. They were very slow and inefficient, and they didn't have any collaboration. So the vision to make in GDS Factory is to make the chip design processes accessible to everyone. So the main reason is to be easy to use and fast. So over the last 5 years, we have reached over 2 million downloads. And just to give you an idea of how fast the tool is growing, you can see that in the last 5 months, we have 500,000. One of the reasons for this growth is that we provide foundry PDKs, because most of the chips that we're currently making, most of the people are using GDS Factory, and they need to have a PDK from the foundry. So the PDK from the foundry contains the layer information for the foundry, and it also contains the building blocks for each foundry. So another of the great success is that because it's a community-based project, we have achieved, I think we have more than 66 contributors today. So it's open for people to contribute to the project. You can just make a fork of the repo, and then you can, if you want, you can share your improvements. But you can always keep them private if you want. So it gives you the possibility of sharing any improvements, and you can also leverage the community. So we have a very active GitHub forum where people can ask questions and people can answer questions. One of the things that GDS Factory makes different from all the other tools available is that it does end-to-end chip design. So it not only does design, but it allows you to run verification, which means so the design will be the layout part and the simulation part and optimization. So this is where you define the devices that you're going to put in the mask. Verification makes sure that what you have in the mask is going to be manufacturable, like DRC, design rule checking. So the foundry will accept your devices only when they pass DRC. LVS, it means layout versus schematic. So you have to make sure that your design intent, which is your schematic, matches your implementation, which is your layout. And then you also do the design for manufacturing if you want, where you can study that your devices behave well over the manufacturing corners. This means erosion, dilation. So yeah, this is part of the verification. And then finally, validation. Validation, GDS Factory allows you to define what your test sequence are going to be. So when the chip comes back, maybe 3 to 6 months after you send the chip to the foundry, the chip will come back. And sometimes you forgot what you did with that chip. So we have a way to define in a spreadsheet, like a CSV file. You can define what are all the devices under test, what are the locations in X and Y, what are the ports for those devices, the ports that you want to put light or put electricity in, or put voltage or current, and then it will define also the test sequence. So it's the only tool that provides an end-to-end design flow. Why do we create a GDS factory? Because all the other tools out there were very slow and hard to use. So one of the comparisons, for example, GDS Pi was a very popular academic tool. So you can see the speed of GDS factory compared to the GDS Pi or like Ipkeys or Nazca or other tools that are purely written in Python, is that we have a speed improvement up to 200 times faster in some operations. So you can see from 20 to 50 to 200 times faster. And this makes the usability much easier. And this is thanks to KLayout being built on top of a library called KLayout. So we're using the Python API of KLayout to do all the geometric operations, which sometimes can be heavy, like a XOR. Like you can see here, some of the XOR, flattening, read and write GDS files. So when you do big Boolean operations or big RDS, read, I think someone has the audio. Okay, yeah. When you do big GDS read or write, or you do big Boolean operations, you will notice this difference. So basically, KLayout, to put it easier, you can see it as it's an extension of the KLayout Python API that allows you to do more than layout. A lot of times when you do layout, you also need to do simulation. So we have made that interface from the layout part to other simulation, verification and validation. So here we can explain it. You can see it in this slide. So you can describe your geometry in Python code. This makes it very easy to reproduce and very easy to share and very easy to add complexity by containing small pieces of code that can be reused for doing different things. Here's an example of how to describe geometry in Python code. Traditionally, this geometry has been drawn by hand, but then it's very hard to make sure you capture those clicks into a program. So instead of drawing things by hand, we define them in Python code. And this will allow you to run this Python code and generate some CAD files. And this could be like a GTS file, this could be Oasis, this could be a PCB like Gerber file, or this could also be an STL file, which has the 3D geometry. So in the same way that we can create CAD files and visualize them, you can also run simulations in your preferred simulation tool. And we support many different simulation tools with the same API, which means the same function calls. Like for example, we have a function called write S parameters, which S parameters is some simulations that we do in photonics, RF. They're very common to describe the relation between input and output fields. So in the same way that you do write S parameters numerical, you can do write S parameters tidy 3D or you can write these parameters using an open source MIP. So we make that very easy for you, that you can interface with different tools with the same language and the same syntax. So we have many extensions to open source and proprietary tools. So you can see we interface with tools that are for device simulation, like for example, like FemWell, it's a finite element solver. We also have DevSim, which is a TCAD solver. Palas, which is made by AWS, which is an an FEM solver for basically this is very similar to HFFS. We also have eigenmode expansion, FEM with Elmer. We also have Tidy 3D and Numerical and MIP. We have something, the Luminescence AI. We have F3DZ. And we have also circuit simulations such as SAX and Excise. But we also can interface with things like Cadence, with Spectre RF, thanks to being able to create spikes that are interchangeable. And today I'm going to show, because this is kind of a workshop, so I was planning to do an example of how to define geometry. So we're going to first, we're going to be using a generic PDK, and we will be also using this open source Cornerstone PDK for some other examples. So we're going to load, number one is you load the technology information, which is the layer information. Number two, we're going to run simulations. So I will be doing a device simulation, like using FemWell. And I will be also doing a circuit simulation using SAX. Number three, we will do verification. So we will do the DRC loop. I won't run LVS this time, but we will be showing DRC. And finally, I will also show how to export this CSV file for automatic testing. So this will allow you to define device port locations and measurement settings. And yeah, I think this is the end of the presentation. I have a QR code too. If you guys want to get the slides or learn more about GDS Factory or get included into the mailing list, you can also scan this. Any questions so far before we do the interactive part of the workshop? I don't know if people are here. Question. Oh, yeah, I see something in the chat. Okay. Hi, we're gonna. Oh, okay. Yeah, I think this will be probably at the YouTube channel that they have. I think Zenchi shared some QR code, so you probably can subscribe to the YouTube channel. We also have, if you go to the GDS Factory website, we also have a YouTube channel here where you can see similar recordings. So we have been, there's many universities where we have organized a similar workshop, the one we're doing today. And some of those videos are shared in this YouTube channel. I also highly recommend going through the documentation. So you will see that we have documentation about how to get started, how to do layout, and how to do schematic-driven layout, or schematic is also important. This is what captures your design intent. It will also talk about PDK. So for example, you can see generic PDK, you can define layers and thicknesses, and this will allow you to convert your 2D component. Like most of the time you're looking at the components here in K-layout in 2D view, but this will allow you to see them in 3D. And this is what will enable to do like component device simulations. So yeah, I would recommend going through this layout. Today we will be focusing mostly on the GDS Factory training. So we will run these notebooks. So we will have a brief layout tutorial. We will do some DRC, and then we will do some device simulation using finite element mode solver. We will simulate the efficiency of a heater. And finally, we will do like a filter, so we will take from FTDD to a whole circuit simulation so FTDD will allow you to compute the S parameters of each building block, and then we will connect all the building blocks from a filter to basically see the waveforms response of this optical filter. and then we will change the parameters of the filter, like the delta length, and we will see how the spectrum changes. And, okay, yeah. So is there any questions? We can start with the. A lot of messages. Yeah. Okay, similar. Okay, nice. How is it interface with Lumerical? Yeah, so Lumerical, we basically have used the Lumerical API. So if you go to the documentation, if we go to the plugins, all the extensions are part of the plugins. So if we go to the Lumerical F3D, for example, you will see here that we have a function. If you pip install G plugins, you will basically be able to call these functions like G plugins dot numerical dot write as parameters underscore numerical. So first thing, you need to create a session, and then once you have a session, you will be basically you can import this plugin as sim, and then you will use this F3D to basically write as parameters of a component. So in the end, you can modify everything that you do through the numerical GUI. You can do it through scripting, and this will save you a lot of headaches because it allows you to define your geometry once. So you don't need to lay out two times. You don't need to lay out one time in GDS, one time in numerical. This directly from the layout, from the GDS factory ecosystem, you can drive both the layout generation, the GDS generation, and the simulation. And this will basically allow you to get the results. For example, like let me show you the one with tidy 3D, which we have maybe a bit more documentation. So this is the same thing. We get a coupler ring. We directly get a tidy. So we directly, thanks to the plugin, we directly convert it to a tidy 3D component. And then this will allow to visualize the simulation. It will visualize the different cross sections to make sure the materials are correct. You can also look at the mod monitors where you're going to excite and where you're going to measure these parameters. And then we can just call the function called write as parameters. And then you will be able to plot as parameters. So you can see the coupling efficient of this coupler. You can also plot the simulation. You can also make sure the modes that you want are the correct ones. Here you can even see it even supports sidewall angles. And finally, you can do basically 3D and 2D. And you can even see like it even allows you to study manufacturability by adding erosion and dilation. And you can also run jobs in parallel. So this is basically, the nice thing of this is that you can run a full PDK library, and then you can get all these parameters for all your PDK elements. So you can see all these simulations are automatically set up. Does it answer the question? Let's see if I... Okay, yeah, nice. Perfect. Yeah, we can do the same thing with creating couplers. So what I wanted to show in the beginning is like, let me do, so let me start with something very basic. Let's start creating a component in GDS factory, another polygon. And then we're gonna run show. And this will basically automatically, once I run this file, I use Python demo MIT, and then I see here I have a component and I have some polygon. So it's very easy to define a component is like a canvas. So in the canvas, you can draw polygons in different layers. I can, for example, change layer 1 to layer 2. And this will basically change the layer from the Wege layer to another layer, which is the slab. This is using the generic PDK from Lucas Korstowski book. So another thing we can also do is we can do a reference. So let's add a reference. So the way you add reference is to c.addRef, and I'm going to add a reference to a pen, and I'm going to add a reference to a MZI. So this will basically, instead of a polygon, it will add a reference to a pen. Let me put here. You have the pen and the reference to the MZI. So these are basically two references drawn inside the canvas. The nice thing of reference is that you can put thousands of reference, and you will only keep the object in memory one time. It's like a pointer in memory. Another thing I can do too is I can connect for example, the pen has ports. So I can actually, if I do show as new top, you can see the pen. I can see the port. So I see the O1 is the input of the pen, O2 is the output of the pen. I can also do the same thing in the MCI. I can show the ports. The O1 is the input of the MCI. The O2 is the output of the MCI. So now what I'm going to do, I'm going to connect the input of the pen to the output of the MCI. So this is like Lego. I'm going to connect one Lego block to another Lego block. And this looks like very simple, like not just an MCI with a pen. But it's very powerful because I can define a function called MCI with pen that's going to take some arguments, return C, then C equals MCI with pen. I can make it parametric. Let's say by default I was using 10 as the pen radius. But let's say I want to make multiple of these. I can do, for example, radius 10, or let's say I want to make 100. This will automatically change the radius of this pen. You see, now it's 100. So it's a very easy, intuitive way to describe your components. Another thing you will notice here is that we have this unnamed 0. So something I think is very useful is to have this decorator will be automatically name the function. So instead of unnamed 0, you will get MCI with bent and then the parameter we are passing, the 100. This is also highly recommended. This destination is not the deprecator anymore. I also do it like this. The second thing we're going to do is if you want to interface with the outside wall, do you remember, I don't know if you remember that this band, as this MCI had ports. So what we're going to do, we're going to do also add ports to the component that we are given here. For example, the input is going to be the MCI 01 and the output is going to be the band 2, the O2 of the band. So when I write this, it's the ports are not really visible here because the ports are things in the GDS. But I can use this show ports, and it will show me O1 is the input now of this MCI with band, O2 is the output of this MCI with band. And this allows you to do things like, very nice. For example, let me say I want to also add, I can do C equals GF routing at fiber array. So this will automatically take this MCI and then add a pen, add a fiber array. So if you want to automatically test this component, you need to inject light in and measure the light out. And we can also put these loopback structures. You can also remove if you do with loopback equals false. It doesn't have that loopback anymore. So yeah, no, there's no more loopback. So it's basically a very nice way to start defining your chip components, like from device to circuits to systems and even full reticles. So I think let me see if any question before we go to the next part. Can you show how to add ports to custom component? Oh yeah, perfect. I think we just did that. How to handle the alignment issues with some curved polygons are not integer on grids. Yeah, this is something, the alignment issues are something that we had in a lot of the GDS Factory. So we just released a couple of months ago GDS Factory 8. So most of the issues people had in GDS Factory 7 and all the previous versions is that we were using floats to represent the polygon points. So one of the biggest problem of that was basically that GDS, it works on a manufacturing grid. So GDS, everything needs to be snapped to 1 nanometer. So the problem of using floats is that you have higher precision than 1 nanometer. And that's very dangerous because you can end up with 1 nanometer gaps. So in GDS Factory 8, we make sure that everything is snapped to grid. So we have here, if you go to the layout, we have this, there's a lot of grid snapping problems on previous versions of GDS Factory. That's what I highly recommend updating to 8. So for example, this is clearly explained here. We have two waveguides. One of the waveguides has 1.4 nanometer length, so it will basically round to 1 nanometer. So you have, instead of here, you have, you were trying to do 1.4, but because this 0.4 is not to the next grid, it will basically go to 1. So it's basically rounding to 1 nanometer. And the 3 one is correct. So this one is defining this. Oh, no, this one is doing 1.6, sorry. So we're trying to do two polygons here. One polygon with 1.4 and 1.6. And they will basically, you will round to the nearest grid point. And a lot of people complain about this. We had ways to fix this or mitigate them, but in GDS Factory 8, we do it with different components that are basically components. We call it virtual instances. So we have components that they will snap to grid at the end. This is more of a complex topic, so I will just say that in GTS Factory 8, we have solved a lot of these problems by snapping early to the manufacturing grid. And you can see most of the tutorials. I highly recommend this. You see, this is the last tutorial, so it's the most advanced. But I highly recommend for people to start tutorials from the beginning and then only go towards the end when they're more confident with the early concepts like component, the polygons. This is what we were showing before. So yeah, did I answer the question? How have been with? Let's see. Nice. Let me see if I can follow. If not, I need some help. Like, how to prevent numerical? How is it possible to import a structure from numerical? Um, Importing a structure from numerical, it's usually the other way around. So you basically from GDS Factory, you generate the numerical simulation. So, and then you can get the feedback loop. So you can basically use GDS Factory on the design loop. Um, how to define a waveguide of the MCI? I want to have a specific waveguide. I think what they mean here is it's a waveguide cross section. So a lot of times I saw there was some issue also today. We are using the generic PDK component, but a lot of times here you want to have maybe instead of radius you want to have something like a cross section. So cross section, it's also it's a medium level complex circuit, but you can see we can go through it together. So when you define paths are basically a collection of points, and you can extrude these paths with different layers. For example, the simplest extrusion is to extrude the path with one layer and one width. But you can also do things more complex where you have a cross section that has basically a layer, so it will have basically a complex layer. And then it has different port names. So we can do something like this, or you can do things even more complicated where you have things, you can extrude a layer with a width and there's a component along the extrusion. So yeah, it can be very complex. But I'm gonna make a, let's say you want, for example, use, so for example, like, I don't know if you notice here, but the default waveguide width on the generic PDK is 500 nanometers. So you can see here. But let's say you want to use, instead of 500 nanometer, let's say you want to use 1 micron. So one way to do it is that you can define a cross section. So let me make it something called strip wide. So I'm going to create a partial of cross section strip, and I'm going to use the width of, and then here is going to strip wide, and I'm going to pass here the cross section argument to both MZI and see. And then I'm gonna just do the MCI with pen, so it's a bit simpler. Let me see. Or with mismatch. Okay, so you see here you can see some of the dangers of like doing this. The problem here is I'm trying to do like a live demo. So the MCI is somewhat of a complex component. So you can see it has many arguments, and it has cross sections, and it has traits and bends. So they have also cross section. So what happens when people when you want to do this, where you want to start modifying the cross sections, the best thing is to define a PDK where you redefine the strip waveguide. So for example, let's go to a PDK where you can do C PDKs. Let's go to the CSPDK. So this is a CSPDK where we're going to do modification on the stray waveguide to use a different cross section. For example, let's go for silicon nitride 300 nanometer. So if we go to the technology, you see here that we have defined cross sections that use a different width, different radius, because the nitride is less confined. You need to make it's wider, and the bends are less abrupt. So here you can see we have customized all the components here. So we have components such as, yeah, you can see we have the technology defined, and we also have a bunch of cells. So we have components like an MZI, and you can see the MZI, we're using the MZI cross section. So this will allow you to for example, let's define a main function, MZI, NZ. So we also have a nitride C-band MZI and a O-band nitride, NC from nitride NC and NO for nitride O-band. So this allows us to create an MZI that has a particular input MZI, MMI, particular output MMI, and it also has a different width. So the width is 1.2. So I rather recommend people when they start modifying cross sections to create a new PDK. Like I've seen a lot of issues on GitHub of people trying to take the generic PDK and only change a few things. So that usually doesn't work because if you change only a few parameters of the MZI, you saw what we were getting. We were getting a width mismatch. So basically, this means that two waveguides have different widths, and GDS Factory will. It used to raise a warning, but now we do error because it's very dangerous to have different widths connecting components because it can create reflections. And, so yeah. 200 element. I think we already covered the polygons border. Can you show how to apply? I already did that. Okay, what happens if we call the MCI with VM function 3 times? Oh yeah. Does it make 3 on the object? Yeah, this is a question like so you can call the function 3 times, and this is also something that's also nice to show. Let me see if I can find the previous. So I'm gonna go back to the demo MIT. You're gonna see also one of the advantages of the cell decorators if you call it times. So I'm gonna see compiling component. I'm gonna just print this. Let me just go back to the default cross section. I can do strip. I think this should be. Let me see if this works. Yeah. So one of the advantages of using the cell decorator is that if you can see I'm compiling here one time, but if I compile the same one 3 times, you only compile it once because then uses you get the other ones from the cache. But I think something you may, I don't know if you're referring to another thing, but another thing you can do is you can create copies of a component. So for example, like let's add 3 reference. A lot of times instead of c.add_ref, so ref1, you will see that we use another notation where we do this. It's a bit shorter. So these two things are equivalent. I don't know which one is more clear. I'm gonna go with the first one because that's the one we show it. But the nice thing of references is that I can move ref2 y mean equal ref max plus 10. We also have this d. So in the GD Factory 8, we have d because we use it for integer. Like this is a layout notation. So now on the MZI, we have 2 reference to the same MZI. So you can see in memory, there's only one MZI, but both of them are referencing to the same component in memory. You see, when I disable one, I disable both. So you can do this. I think you were asking for 3, but yeah, you can do as many as you want with this. flatten method. Yeah, flatten method. Basically, we can do flatten here. So flatten will basically absorb. It removes the hierarchy of the component. So you can see before we have hierarchy. So this just removes the hierarchy and basically adds all the points into the GDS. So if you have to reference to the MZI, this only had to save this MZI in memory one time, and the other thing was just a reference with X and Y and rotation. But if you flatten it, you make the GDS bigger because all the polygons don't have hierarchy. So it's basically removing the hierarchy. So there's different reasons for flattening the GDS. I usually don't do it unless it's necessary for things as LVS, where you basically want to have only one hierarchy level for a component. I usually don't do flattening if I can. It will make your GDS smaller. Mm. Yeah, nice. Okay, yeah, perfect. I already catch up. I thought there were a lot of questions. Sorry. Okay, nice. All right. So we've done some simple P cell. So we have a lot of samples also, the GDS factory samples. So if you go here, we could go through a lot of things, but I want to show some cool examples of how to do things like a big device, for example. Like, let's say you have a device with lots of ports, and then you want to automatically route them to a fiber array. So this is something in GDS Factory can help you a lot, because we have this basically add fiber array that will basically automatically add fiber array. Yeah. So we basically add the components of fiber array. We also have this, they have an electrical version of this where you can actually do the same component. It's a similar square component with lots of ports, and it will automatically route it to grading couplers. So to paths, sorry. The other thing I wanted to also show is that we can also do things very fast. Like, let's say one of the reasons I really like the factor is because it's very easy and very fast and very easy to use. So let's say you want to do 100 Mach-Zehnder interferometers. I can do 100 Mach-Zehnder interferometers in a second on my laptop, and these are 100 different Mach-Zehnder interferometers. So yeah, if someone has questions about the speed, they can try to do this in other tool, and you will see how slow it is. And they're all basically placed on a grid. Something I also wanted to show, so we already talked about this cornerstone PDK. So I'm going to show some examples with the silicon 220 thickness, basically cornerstone PDK. So I'm going to do an MZI, I'm going to extract the netlist, I'm going to run a circuit simulation. So let's start with a delta length of 10. I'm gonna visualize the GDS here. So I'm running this file. It creates an MZI with a delta length. So you see it has some longer arm here. It's extracting the netlist. Every of these elements, like the coupler, the band, the waveguide, have some S parameter models associated to it. And then you can make a circuit simulation where you can see the whole spectrum versus power. And I'm going to do another one with, instead of 10, I'm going to do 100. So this is going to make this delta length much bigger. So instead of 7, it goes all the way here to almost like 50 on this side, 50 on this side, so it's 100. And it does a more tighter spectrum. Okay, yep. So another thing you can also do is you can do circuit simulation where you have two MCIs with a route in the middle using this route bundle or route single. So you have two MCIs routed, and then we run the circuit simulation of this first MCI connected to the second MCI, and you see the spectrum of both. So you see whether the 10 has only two fringes, and then the 100 has a lot of fringes. So basically, the transfer function is the multiplication of both. The other thing I wanted to show is also like it can also allow you to do verification. So test samples. So if you do verification, it will basically, you can see before we're getting disallow with mismatch. So by default, it will disallow with mismatches and it will raise an error. But if you want to make an error on purpose, you can. And then we're gonna create two components that are mismatched. We're gonna allow the mismatch and we're gonna try to run a connectivity checks. So this is the type of thing that if you do a lot of this, it's very hard to catch. That's what we decided to forbid them by default. So by default, it will raise an error. So you see, it's doing a width mismatch between the wavegates here, at the input and at the output. So it's, and this is one of the nice things of GDS Factory because we're completely built on top of klayout. We can call natively functions from klayout. Okay, so this is pretty much most of the layout part. Let me see if there are any new questions. Oh, there's more questions. Let me see where we are. Can I make this bigger? I don't know if I can make the chat bigger. Yeah, let me try to make it. Yeah, nice. Okay, so let's see. Okay, how to buy a component? Yes, we already did that. Can you display fundamental? Yeah, okay, nice. Does the netlist generation uses port that touch each other on the GDS? Yes, correct. Yeah, the netlist generation, the netlist extraction is making sure the ports are touching. So, yeah, if ports have the same X and Y, that's basically a connection. And you don't need to use the connect method. You can have implicit connections where you can move components that are you can move a waveguide to be at the right or another waveguide. As long as the ports have the same X and Y, they will be considered connected. But I usually recommend connected because if you do things with X and Y, it's very easy to leave some offset somewhere. Or like, let's say you grow your component or you add some cladding and the cladding it goes via the component. It's a bit dangerous. So I would recommend using the connect because it will do that with check for you. How does it work with non-open source PDKs? Yes, this is a good question. Yeah. So for the NDA, so foundries that had GDS Factory PDKs, you need to contact the foundry and then you can CC GDS Factory community. So you can CC me for the foundry if you, some of the foundries have PDKs, but depending on the person that you talk, sometimes they don't know about the GDS Factory PDK. So you can CC me if you get problems like some of the foundries don't know that they have the PDK. But yeah, you need to be in touch with the foundry for first. You need to sign an NDA. So an NDA is basically to make sure you don't disclose any of the information, the private information from the foundry. And this is also something people need to understand. The fact that GDS Factory is open source doesn't mean that everything that GDS Factory is open source. There's a bit of misunderstanding with open source. So, like same with Python or Linux. Python and Linux are open source, but all your scripts you have on your computer with Python, you don't have to share. So foundries have PDKs with GDS Factory, but they want to protect them to make sure they don't go to their competitors. So you will need to sign an NDA, which is a non-disclosure agreement with the foundry. And once you have that, they can give you access to the PDK. Let's see. Okay. Yeah, that's the support corner case. Yeah, the corner simulation. Yeah, we briefly touched it in the Tidy 3D where we can show erosion and dilation. So the foundry, some of the foundry PDK have statistical models. Some of the foundry PDKs don't have statistical models. So if they have statistical models where they do the sigma variation of the width and the height and the refractive index variation, you can actually do corner simulation. And this is something we have in a tutorial here. If you go to the plugins, if you go to the circuit simulation that I use the most, SAX circuit simulation, this is my favorite one. So we have a layout aware Monte Carlo, which basically, if this assumes some variability of the width, so you do simulations of a waveguide with different width and height, and then we define wafer maps. So these wafer maps needs to be adapted to the foundry standard deviation that they give you. So what's the mean of the variation? What's the standard deviation? And then this will allow you to take a component and then run it with Monte Carlo. So this is running like 100 simulations. You can see the nominal one in red, the Monte Carlo is in blue. But this will allow you also to model things like we can make an MCI that's compact, and this mitigates this variation. So the same component, if you lay out smart with a smart tricks for layout like this one, where you bring the waveguides next to each other, it reduces the variation by 10. But yeah, these are things that you need to run it with these models from the foundry. This will be part of the PDK. See. For DRC, some coupler support to validate the spacing rule. How do you remove filter? Um, so for DRC, some couplers violate DRC rules. So violating, like inverse design, yeah. So these are things that you have to, these fabrication constraints like DRC, you have to embed them on your iteration loop. So if you want to make sure your foundry accepts your design, it needs to comply with DRC. For example, let's say we can also do this together. We haven't reached that part, but I can go into it. It was the next part, but it's actually a perfect transition. So we can you can define your DRC rule text in different languages or different tools. Like GDS Factory allows you to create DRC text in KLayout, and it's as easy as this. It's as easy as rules, check width, what layer, and what value. So this will basically be writing a DRC in KLayout, and then we'll also create basically a layout here for us to test. And then you can do DRC, generic DRC, and then you can see with space, with violations. So you can see minimum width, we have a minimum width, we have a minimum space, minimum header. So you have to make sure you comply with DRC rules. So yeah, you just need to put them into your optimizer, and then you also have to take that into account. So otherwise, the foundry can reject your devices if some of those violations are critical. Uh, is it possible to add the foundry's GDS to a PDK and GDS factory? Yeah. This is basically what the PDKs does. So the PDKs from the foundries, most of them are GDS that the foundry provides. So we just take the GDS, import them, and add ports. So PDK is basically layers with PDK is the layer information for the foundry with the component GDS or black boxes, whether they give you, and those will have ports, the models for those components, so you can actually run circuit simulations, and then the DRC and LVS if they provide an LVS. But these are basically the verification rules for the foundry. Schematic relay assume the component crosses manually inserted into the schematic. So feature direction. This is a really good. Like automatically insert crossings. This is something that people have asked in the past. So what Chachi means is that when you're doing routing, sometimes there's like crossings that can happen, and those crossings can be detected and replaced with a low loss crossing. So yeah, this is things that some people have asked. But people also need to understand that the GDS Factory is an open source project. Like we have a few things on the roadmap, but it depends on the community to develop these features. So if someone wants to work on this, I will be happy to point them. There's a few people who have worked on this on the past, and they say they may be able to contribute this. So yeah, we'll see if we have that available soon. Is there any GPU accelerated open source plugins? Yeah, we do. So if you go to the plugins on FTD, So we support two GPU accelerated plugins that support. One of them is FTDZ from Spins Photonics, which is a startup out of Stanford, Jelena Vukovic lab. So this one is using GPU acceleration in FTD. And we also recently made a luminescent.ai extension. It's not documented yet, but maybe that's a good time where you can actually open an issue and then create an issue of, say, add documentation for luminescent AI. I think it's spelled correctly. It's luminescent AI. I think it's a Paul Cheng, the one who made it. So these things are, all the extensions there are constantly new ones coming up, so you need to keep an eye on the GitHub. And this, okay, I think, oh, ceviche. Yeah, we could have ceviche. Yeah, these things are you guys need to understand that this is an open source project. So, like, if you guys want integration with ceviche, the best way is to you either do it yourself, or you find a friend who can help you do it, or you pay someone to do it for you. So this is kind of like but the nice thing of it is that you can pay anyone to do it. It's not only the company who made it keeps it secret. So it's up to the community to develop and maintain these plugins. And if we can also quickly show like mode solving. I think we have only 10 more minutes. But the mode solving, we have two mode solvers. One FEM with FEMWell. That basically the difference with the FEM and FDFD is that you basically this one is basically the grid. It's like a triangular, so it basically you can capture small changes. You can see how the mesh is created. You can also plot the epsilon. So this is the refractive index. You can see a silicon waveguide of 3.4 index rounded by 1.4. This is an epsilon. And you can also compute the electromagnetic modes. And then you can print the T faction and show the real and imaginary part of the mode. You can also plot the intensity of the fundamental mode. So this is mode 0. You can also plot this is the fundamental mode, and this is second order mode. So you can see two intensity lows. And can also we also have a mode solver with the tidy 3D. So tidy 3D, you need to understand that it's like numerical. You need a license, so it's a proprietary software. But the mode solver is open source, so you can use the mode solver even if you don't have a tidy 3D account. And it's the same thing, just that instead of triangular mesh, you see it's basically a fixed grid mesh. And this is what we use on the eigenmode expansion meow. And you can also set the width of the waveguides and compute like different modes supported as a function of width. And then dispersion. Oh yeah, you can see it's computing the modes. And the other thing you can also see, we have also the band loss calculation. So you can also compute band modes and compute the mode overlap with the fundamental mode. And this gives you an estimation of what's the mode, the loss through a band. You can also, yeah, this one may take some time, so let me just stop it, and then we're gonna move to the FEM because I think we only have 5 minutes. I wanna also show the MZI. For thermal, we also use FEMWell for thermal simulations. So this is basically taking a heater. You can also see it in 3D. So this is a metal heater on top of a waveguide, and we are going to look at the cross section of the heater. So as we flow current through this metal, there will be some heat distribution across the chip. So you can see we have, see if we will see the cut. We see a waygate and a heater on top. And then what we're doing is we're changing as we apply current. We also calculate the refractive index change. So we basically solve the modes for different current in the heater. And then the last simulation that we're going to do is this MCI. So the MCI is basically an interferometer that you can, we're going to model with a combination of a mode solver, and we're going to do the FTDD. So we're going to compute the FTDD. So the mode solver is for the straight and wavegate calculations. We will compute the propagation, the index, refractive index propagation. Then we compute these parameters with FTDD, and then combine that. We're going to do a coupler, input coupler, the bend, the straight, the output coupler, and then we compute the S parameters. So we extract the netlist, create models. So these are the S parameter models of every component, and then we do a circuit simulation of this MCI. And then we do another MCI with different delta lengths. So the first one, the delta length was 10, and the second one, the delta length is 20. So you see the 21, we have half the FSR. And you see the simulation was very fast because we stored this NPZ, so the simulation actually didn't have to run. So this is a trick that allows you don't run the simulation 2 times. You can store them as NumPy arrays. Okay, so this is the end of the demo. But let me see which one. Yeah, we can access the file. Yeah, all these examples are part of the training. So if you go to the GTS Factory Photonics training, all these files are on the GitHub repository. So you can access all these notebooks here, even the NPZ file of the MMI that I talk about. That way you don't have to get a Tidy3D account. This is basically it's like the results are already here, so it will load the results directly. Otherwise, you need to it will spend some credits to run that simulation for you. There were some more questions before. The corner K, TRC, yeah, I think schematic layout, GPU, yeah, ceviche, we talk about that. All the generic component usable with the default dimension. How can I get the specification of one thermal phase shifter, for example? Do you need to simulate it yourself? Yeah, like in the end, for all these things, you have to. These are basically examples, so you need to adapt them to your particular technology, foundry, and as well as design. So in the end, you need to do the design. Like for example, if you go to the plugins, if you need to create like not only the simulation, but in the end, you need to add that simulation to a circuit model. So here in SAC simulation, we have this phase shifter model where we have an MCI similar to the one we show, but it has a heater on top. So you need to create a heater model where you have, depending on the voltage that you apply to the heater, you will have a different phase shift. And this will allow you to do an active component. So these are the things that you need to do it if you do your custom components. The foundries provide you already, most foundries provide you already with these elements. So if you work at the device level, most of the people optimize the devices. If you want to just do it at the circuit level, you can just take the elements for the PDK if they're good enough for you. If not, you need to spend some time improving them. Do it remote solvers, computer visualization? Oh yeah. Yeah. This is so there are actually both of the mode solvers. Yeah, maybe I think firmware we have this automatically from the cross section. We can actually simulate. I think for the Tidy3D mode solver, you have we have a function to automatically generate that for you. I don't think it's using the cross section definition. can you export? Yeah, for 3D geometry, we only support STL. Mm, I'm not familiar with Parasolid or Step, but yeah, if someone wants to take a look at it, we'll be happy to yeah to take a look. If the plugin of the heater open source, yeah, this is fully open source. So if you go to the device simulator, and the one I showed today, it's based on this Femwell plugin. So Femwell is a pure open source project where it's basically a multi-physics, multi-domain where you can do PN junctions, thermo-optic phase shifter. This is very similar to the example I was showing, where you can compute the 3 milliwatt per pi phase shifter. You can even do transient simulations of an RC heater. It has like lithium niobate phase shifter. So yeah, this is a really good example, a really good project. So I highly recommend also going through these tutorials, and it even has theory. So I hope people, especially at universities, start teaching with these kind of materials, because you can even go into the code and see how these things run. So that's the best way to understand the physics of the devices, is to be able to look at how these are basically coded. And we have like it has things as dispersion curves, and like crosstalk, and yeah. Okay, and the last question. Thanks for the super. So play more dances with dances. Oh, okay. Uh, yeah, yeah. Mostly use Femwell. So yeah, I also don't use SolidWorks. I understand these things are very popular CAD files, but yeah, for I'm mostly doing chip design. So for chip design, the most populars are GTS and Oasis, and for simulations, I think the most popular is STL. But I don't even use STL myself. It's only for people to show that we can actually, as part of the layout, we can write it as a GDS or like as an STL. I think if you want a 3D print, I think you use STL. So if you want to do other things, like import it to Blender, and I think there's also other Python packages to doing that. So maybe you can. But yeah. Any question? You guys can also talk. I mean, mostly, this is the first time I give a talk and people doing on the chat. But it's interesting. Yeah. If not, thank you very much. I hope you enjoy the workshop, and we're looking forward to hearing you how you use this factory. And yeah, I basically use a lot of MATLAB when I was at school, so I switched to Python, and everything runs better and faster. So I hope you guys also can start using open source tools to make your work, and also understand how things work. It's also very good if you're pushing the boundaries, like doing research, to be able to do like things fast and being flexible.
Okay, yeah. And the timing is just about right. Thank you. Yeah, thanks for everyone joining this seminar, and especially thanks Joaquin for the great interactive tutorial and also sharing with us the capability of the latest GDS factory. I would say feel free to connect with the speaker for more offline discussion on GDS factory, and also I just welcome everyone to just contribute to our open source Photonic EDA community. Right? This is really fantastic work. And of course, the slides, videos will be online, and I'm pretty sure this workshop will be very helpful for researchers in this field. And also, please share with your friends if they cannot attend today. And welcome to subscribe our mail list and also follow our future seminar events. Okay, I'll say this concludes our today's events. Thank you again. Thanks, the speaker.
Thank you.